Hi, hello, welcome back to our channel Chemistry with RK. Firstly, I would like to request, if you're new to the channel, please do subscribe and then don't forget to click on the bell icon to get continuous regular updates. In this video, I'm going to start. I have chosen an inorganic chemistry concept called as complex compounds, which is very much important for any kinds of competitive exams. This chapter has a huge weightage in IIT-JEE or advanced or NEET or any of the state level competitive exams. So if we particularly take this complex compounds for our JEE mains or advanced, we'll obviously get one or maybe two questions. If we go for NEET, we will obviously get two or more than two questions. So which are very easy or which are quite related to periodic classification chapter. So in this particular concept, in this particular chapter, I am going to include some of the concepts which are related to periodic classification also, so that you will enjoy, so that parallelly you can learn the concepts of periodic classification. Before we go into the concept complex compounds, it's very important to understand the terms involved in this. So here I have given the list of compounds which are very important to understand. So the complex compound, central metal atom, ligand, coordination sphere, dative bond, coordination number and counter ions. So in this video I'm going to explain about all these terms in detail so that the next coming lectures can be easily understand. Okay, so first let me take an example. You must have come across this type of compounds K4FeCN taken 6. This is an example for complex compound. And now where we are going to call this square bracket part is called as coordination sphere. So yes, this square bracket part is called as coordination sphere. And inside the coordination sphere, we could see there is a central metal atom and there are some group of atoms which are coordinated to the central metal atom. So in this particular complex, we can see iron behaving as a central atom, where 6 cyanide groups are attached to iron through coordinate covalent bonds. So I am here using different terms. So just give me some time, or you just feel comfortable to understand. So I'm going to give completely with different examples, so don't worry about it. Yes, firstly I would like to tell the coordination sphere is nothing but the square bracket part is called as coordination sphere, or it is also called as coordination entity. Inside this coordination sphere, we can see there is a central metal atom. In most of the cases, the central metal atom could be a transition metal. And now this particular central metal atom is going to combine with or bond with some atoms or group of atoms through coordinate covalent bonds. So here we could see 6 CN groups are attached to iron inside the coordination sphere, where the 6 defines the number of coordinate covalent bonds which are going to form with the iron metal. And outside the coordination sphere, we could see here 4 potassiums. We know that generally the counter ions are used to balance the charge on the coordination sphere. So what does it mean actually? Okay, if you just go with respect to potassium, potassium has a +1 charge. On each potassium has +1 charge. And now such potassiums are 4 here in this complex. So overall positive charge will be +4. And to balance that +4, this coordination sphere is going to have a -4 charge. Hope it is clear. So what I mean to say is, if suppose let's say if we try to dissociate this complex, we are going to get K plus ion, and then we are going to get, there is a complex ion which is K4FeCN6. And now since we have a +1 charge on potassium, we expect a -1 charge on the coordination sphere. But please make a note, here we have 4 potassiums, so we need to take 4 K plus, so that the overall positive charge is going to be +4. To balance this +4, this coordination sphere must be given -4. I hope you understood. The role of counter ions is to balance the charge on the coordination sphere, which is very important. If we are going to miss the charge on the coordination sphere, then we are going to get so many difficulties in understanding the concept. So hope you understood. Yes, if you have any doubts, and then from the next videos, from the coming videos, I am going to post the necessary PDF material in the link. So please do watch, and then please do download, and then please do make use of that PDF. And then if in case in that PDF also, if you have any kinds of doubts, please do comment your queries in the forms of comments, so that I can able to reply. Okay, let's continue. That is coordination sphere. So overall I have defined few things here. That is, coordination sphere is the square bracket part. Coordination sphere is the square bracket part, or it is also called as coordination entity. And within the coordination sphere, we are going to have a central metal atom, and then with this central metal atom we are going to see some some number of maybe atoms or group of atoms attached to the central atom, and those particular groups are attached to the central atom are called as ligands. And then how many such ligands are there? Actually in this particular example we can see 6 CN groups are there. So which mean that each CN group is going to form one dative bond or one coordinate covalent bond. So here we have 6 CN groups. So the overall coordinate covalent bonds around the iron in this particular complex will be 6. That number of coordinate covalent bonds around the central metal atom defines the coordination number. So I hope you understood what is the coordination number for iron in this complex. It is going to be 6. Hope you understood. And now let me just define, or let me just give you a definition, proper definition for the term complex compound. So the complex compound is nothing but the compounds in which the central metal atom is going to have going to form a more number of bonds than what we expect. So beyond their valency. So one of the very important properties of transition metals are they forms, or they shows, or they exhibit variable valencies. So here iron is going to show 6 bonds through dative bonds, we know. Hope you understood. So finally what we can conclude is complex compounds are the compounds in which the central metal atom shows valency more than what we expect. So beyond its valency it is going to form more number of bonds through dative bonds. That is a very important point to understand. So in this particular chapter, in the entire complex compounds, we are going to deal with most of the dative bonds. Okay, so just let me go with the terms here. Complex compounds, yes. So general representation of complex compounds I am going to give here. So that is, counter ions are going to be present outside the coordination sphere. So we may have any number of counter ions, there is no problem with that. So counter ions will be present outside the coordination sphere. And inside the coordination sphere, we are going to have a central metal atom bonded to some atoms or group of atoms which are generally called as ligands. And now this N is nothing but the number of ligands actually. So here N defines the number of ligands. Hope you understood. It is not only the one of the representations. There is another representation also where the counter ion could be present after the coordination sphere or metal complex. Here we can also have metal combined or bonded to ligands, and then we can have counter ions. Yes. Sir, what is the exact difference between the first and second representations? In the first representation, if you see, the metal, the coordination sphere is present after the counter ions. Here, the counter ions are present after the coordination sphere. What is the difference actually? It's very important. In the first complex compound representation, the counter ions are going to give a positive charge. The positive charge will be given to the counter ions here, and then followed by the complex coordination sphere is going to give us a negative charge. Very important. Whereas in the next second representation, the complex part or the coordination sphere part is given the positive charge, whereas the counter ions are going to get the negative charge. Very important. I hope you understood. So in the first representation, the complex sphere is going to get the negative charge, since it is given negative charge, or since it is getting the negative charge, this particular type of complexes are called as negative complexes. In the second representation, our complex part has given a positive charge. Since it has given the positive charge, this type of complexes are called as positive complexes. Hope you understood. So yes, we are going to understand these terms in detail. So you try to take the screenshot of this. Yeah, here I have taken few examples to explain the terms which we have discussed earlier. So that is actually this K4FeCN6, the whole compound is called as a complex compound, where if you look at the dissociation, 4 potassiums are there, it is going to give us 4 K plus ions. And now since there is a positive plus 4 charge, then the coordination sphere is going to have minus 4 charge. And now since the coordination sphere have a negative charge, the complex is called as a negative complex. Next, moving to this, I have taken CONH3 taken 6 Cl3. If we look at the dissociation, it is going to give us 3 Cl minus ions. And now to balance this negative charges, the coordination sphere need to have plus 3 charge. Now since the coordination sphere has a plus 3 charge, that is positive charge, the complex is called as a positive complex. And now if you look at, this is the entire complex, where this is a particular coordination sphere. Inside the coordination sphere, we can see this cobalt is a central metal atom. We can see 6 ammonia molecules which are acting as a ligands, and then these 3 Cl minus are the 3 counter ions, and then 6 is the coordination number for cobalt in this particular complex compound. Similarly, if you look at this CuNH3 taken 4 SO4, then if you observe the dissociation, CuNH3 taken 4, SO4 will have minus 2, which is sulfate, we know. To balance this minus 2, the complex will have plus 2 charge. And now you please guess what type of complex it is. This coordination sphere have positive charge, then obviously this must be the positive complex. And then moving to the next, K2HgI4, which is so famous, called as Nessler's reagent. Here we have 2 potassiums gives 2 K plus ions, and then their complex ion is, complex coordination sphere is HgI4 minus 2. So here Hg is a central atom, 4 iodines are the ligands, and then since the complex have a negative charge, so the complex is negative complex. And then if you look at the last one, nickel tetracarbonyl. So here, do we see any counter ions in this complex? No, we don't have any counter ions. Since there are no counter ions, there will be no dissociation. In this type of complexes are called as neutral complexes. The complexes which cannot undergo any dissociation, or we can also say the complexes which do not have any counter ions to undergo dissociation. Such type of complexes are called as neutral complexes. Hope everything is clear here. And now please, I just go on asking you the coordination numbers here. What is the coordination number of iron in the first complex? Have a guess. It is obviously 6. Coordination number is going to be 6, because 6 CN groups are there which are coordinated to the iron. And then in the next complex also 6 ammonia molecules are there. Each ammonia gives one particular lone pair, so that it forms 6 dative bonds, so 6 coordination number. And the next, if you look at this CuNH3 taken 4, here we have 4 NH3 groups. Each NH3 group can able to donate one lone pair, so that here 4 dative bonds we can get. The coordination number is going to be 4. So what exactly the coordination number? Coordination number can be easily defined as the number of dative bonds formed by ligands with the central metal atom in a coordination complex. Hope it is clear. If you look at this, here we have 6 ligands, so 6 ammonias can able to form 6 dative bonds, so the cobalt is going to have 6 coordination number. Similarly, copper, 4 coordination bonds, so 4 is the coordination number. Similarly, mercury, 4 iodines, 1 iodine can donate 1 lone pair, so that 4 iodines can donate 4 lone pairs, so that 4 dative bonds can be formed. Number of dative bonds formed by the ligands with the central metal atom in a coordination complex defines the coordination number. So here the coordination number will be 4. And now next if we move to NiCO4, that is nickel tetracarbonyl, each CO can also donate one lone pair. So you may get a doubt, sir, how can we say like the ligand, how many lone pairs it is going to donate to the central metal atom? So that we will see soon in the next video, hopefully. So that is, depending upon the number of lone pairs element is donating, those many number of dative bonds we are going to get. So here, as far as all these ligands are considered, all of them are monodentate ligands, which mean that they can able to donate only one lone pair. So here also 4 CO groups are there. So each CO can able to donate one lone pair. So here also we are going to get 4 dative bonds. Finally the coordination number is going to be 4. Hope it is clear. And then next let me define the term ligands. So how to define exactly the term ligands? The chemical species which have a tendency to donate a lone pair to the central metal atom in order to form a coordinate covalent bond. So very important. So ligands generally they donate electron pair to the or lone pair to the central metal atom. So generally we see the ligands donates a lone pair to the central metal atom. So ligands always electron pair donors, they act as electron pair donors. Generally electron pair donors are called as Lewis bases. So in a coordination complex, ligands always behaves as Lewis bases. Very important. So if you open any of the competitive exam question papers or any of the reference books you have for IIT and NEET, you could see all these questions in the objective part. So please do follow the video carefully and then start doing your problems. So soon I am going to post another objective PYQs, previous year questions on this same topic. So as I have posted in the oxidation numbers and then solutions, molarity, you please do watch my previous lectures on molarity, normality, N factor, stoichiometry, and then even I solved a few questions on solutions from solutions chapter. And then similarly I am going to post the video on previous year questions soon on this particular concept also. And now if you observe carefully, always the electron pair donors will be the ligands and electron pair acceptors will be the central metal atoms. And now hence we can call central metal atoms are going to behave as Lewis acids and then ligands are going to behave as Lewis bases. Hope it is clear. And now if I ask you what is the coordination number of COEN taken thrice plus 3. First my question is, what is the central metal atom in this? Cobalt. And how many ligands are there? How many ligands you can see here? 3 ligands you can see. All of them are same type. En. So as of now we didn't come across such type of ligand En. Actually the ligand En is nothing but ethylene diamine. So ethylene diamine is a ligand where we have 2 nitrogens. Actually what is the structure of ethylene diamine? Ethylene diamine is CH2 and then 2 NH2 groups on both the carbons. Yes, actually this is the ethylene diamine molecule where each nitrogen have a lone pair. Each hydrogen you can see a lone pair. So now what we can understand from this, one such En molecule or one such En ligand can able to donate 2 lone pairs for the dative bond formation. We know very well in one particular dative bond, 1 lone pair is enough. Here since we have 2 lone pairs, this particular En molecule is going to form 2 dative bonds. 1 En molecule can form 2 dative bonds. 3 En molecules can form how many dative bonds? 6 dative bonds. And now what is the coordination number for cobalt in this particular complex? Obviously it is going to be 6. And don't get confused, every time in all these examples if you observe, this number defines the coordination number. So coordination number of iron is 6, coordination number of cobalt is 6, coordination number of copper is 4, and mercury is 4, nickel is 4. So in these examples, directly these numbers, the number of ligands defines the coordination number since they are monodentate ligands. they all can give only one electron for the dative bond formation. But whereas here, one such En molecule can able to donate two lone pairs to form two dative bonds. So here finally what we can conclude is one such En molecule can able to donate two lone pairs to form two dative bonds. So 6 is the coordination number here. So don't just go with this number as the coordination number, then you will be in trouble. So it depends upon the nature of the ligand. Soon that also I am going to give clearly in the list wise in the next coming video. So you please try to understand what is the coordination number of cobalt in this. It is going to be 6. Hope it is clear. Next, let us move on to the next term, coordination number. So what exactly the term coordination number defines about? It defines about the number of dative bonds present in between ligands and the central metal atom in a coordination complex. As I have told earlier, so like if you look at the K4FeCN6 complex, we can have the coordination number of the central metal atom iron in this is 6. So like if I say coordination number 6, then what must we have to understood, that is in between the central metal atom and the ligands we must see 6 dative bonds. Yes, this is the actually if the coordination number is 6, then the expected geometry for that particular complex will be octahedral. And now in the octahedral complex, around iron we have 6 CN groups. You could see 6 dative bonds around it, iron in this particular complex. Hope you understood. And likewise, all the complexes, just let's move to this particular table. I have given few complex compounds and their coordination numbers, and you have to define the coordination numbers for all these complexes. So now if I ask you what could be the coordination number for copper in this complex, it is going to be, as I told you, NH3, one NH3 can donate one lone pair only, which means one NH3 can form one dative bond. 4 NH3s can form 4 dative bonds, then the coordination number must be 4. Hope you understood. And now, next moving to the next one, that is FeCO5. As I told earlier, CO can also form one dative bond. 5 COs are there, then the coordination number must be 5. Hope you understood. And the next, sodium zincate, actually this is called as Na2ZnO4, that is the number of ligands we have is OH, that is hydroxo groups. And now we have 4 such hydroxo groups. Each hydroxo group can able to donate one lone pair. So 4 OH groups can donate 4 lone pairs, so that it can able to form 4 dative bonds. Then the coordination number must be 4. And now this particular example I have taken just a few minutes back, that is COEN taken thrice plus 3, which is nothing but ethylene diamine. One such En group can able to donate 2 lone pairs. Hope you understood. And now both the donor atoms are nitrogens in this particular En. Hope you understood. And now we have 3 such En groups. One En can form 2 dative bonds. 3 En groups can form 6 dative bonds. Even though we have 3 En groups, the coordination number is going to be 6. Hope you understood. Hope it is clear. And then next, I have taken C2O4 taken thrice plus 3. This is called as oxalate ion. This is called as oxalate. And now in oxalate ion also we can see this is the structure of oxalate ion. If you can able to go back to the structures. So this is C2O4 minus 2. Here also we can see 2 donor atoms, 2 oxygen atoms are there to donate. There are 2 oxygen atoms can able to donate 1 lone pair. So one such C2O4 molecule can able to form 2 dative bonds through 2 oxygens. Such C2O4 groups we have 3, so the coordination number for this particular complex also it's going to be 6. Hope you understood, hope it is clear. Yeah, this is all about the term coordination number. And now by using the term coordination number, we are going to, for complex compounds particularly, the hybridization and the geometry is decided based upon the coordination number. So that we will see in the next coming video. Before I end up my video, I would like to request, if you are new to the channel, please do subscribe and don't forget to click on the bell icon, and then we'll soon come up with the continuation video on this of the hybridizations and then the types of ligands and all. Until that, thank you so much. See you soon.